Swayam Prabha. Digital India. Educated India.
So, this is a lecture on a few ligands which are alternatives to carbon monoxide. We have already seen that carbon monoxide is one of the best ligands in organometallic chemistry, because it provides unsurpassed pi bonding character, and people have always been looking for alternatives to carbon monoxide, because carbon monoxide does not exert a significant steric influence, and it is possible to have specific catalytic properties if you can modify the steric properties of the ligand. So, with that in mind, people have been looking for alternatives to carbon monoxide, and today we are going to look at a set of ligands which have come out to be extremely useful in organometallic chemistry and which rival carbon monoxide in terms of some of the properties that they exhibit. If you look at all the carbon ligands, one can see this map where you have carbon monoxide is somewhere here. It is a ligand with a single carbon. There are other ligands which have a single carbon attached to the metal, and you notice that among the ligands which have a single carbon attached to the metal, carbon monoxide occupies a unique position. So, if you focus further on some of these ligands, you find that carbon monoxide can be replaced by Cn minus or alkyl isocyanides. And if you focus further on this group of ligands, which is the alkyl isocyanide group, we can see how this will naturally lead to the set of ligands that we are going to discuss today. Alkyl isocyanides are excellent ligands, and we can see that they have pi accepting properties, because the free ligand has a stretching frequency of 2136 centimeter minus 1, and when it is complex to nickel 0, the stretching frequency reduces by 100 centimeter minus 1, which is exactly what happens with carbon monoxide also. So, there is a distinct advantage for alkyl isocyanides, because you can have some steric influence due to the presence of this AR group attached to the isocyanide moiety. A further note of similarity to carbon monoxide comes when you compare the complexes formed by alkyl isocyanides with positively charged metal atoms. The frequency, instead of going down, actually increases. This is exactly what you find for carbon monoxide also. And this has been attributed to two factors. One of them is the lack of pi back bonding, and the other is the fact that you have a charge on the metal and it influences the stretching frequency through an electrostatic phenomenon. Unfortunately, although alkyl isocyanides are so good, they do have one disadvantage, and the disadvantage comes from the fact that you have a complex, many times you have a complex where the metal is positively charged and the isocyanide develops a partial positive charge on the carbon of the isocyanide. So, the alkyl isocyanide ends up with a charge in the complex where the carbon is positively charged and the nitrogen is slightly negatively charged, and so is the metal atom. So, now we have a problem, because if you have a nucleophile, the nucleophile would like to attack the carbon which is positively charged, and many times you have an alcoholic solvent. The alkyl isocyanide rapidly reacts with it and forms a type of a carbene complex, where the ethanol or the alcohol, ethanol in this example, adds across the carbon and the nitrogen, so that the oxygen adds here and the proton adds at the nitrogen end. So, this is a specific example, but it is generally true that nucleophiles will add on to the carbon in such a way that you have not an alkyl isocyanide anymore, but a carbenoid type of a complex. So, let us look at the alternatives that we have examined. One of them is carbon monosulfide and carbon monoselenide. These are indeed isoelectronic with carbon monoxide and are very good ligands. They have very good pi bonding characteristics, and they have good electron density on the metal, because carbon CS can donate electron density very well. But unfortunately, there is a great difficulty in making them. They are not as good as carbon monoxide, which is readily available in a cylinder. So, we also looked at cyanide, Cn minus, where you could change from CO to Cn and then add an electron to compensate for the number of electrons. That gives you Cn minus, which is identical in terms of electron count to carbon monoxide. So, Cn minus should have been a good ligand, but because of the negative charge, it tends to generate excess electron density on the metal, and so it cannot stabilize low valent metals. So, then we moved on to alkyl isocyanides, but unfortunately, as we have just seen, these complexes hydrolyze very easily, and they generate complexes where you have a carbene, and the carbene has got an NR2 group. In the previous example, we had NRH and a OR group attached to the carbon. So, these carbenes or these carbene complexes are those systems in which you have two heteroatoms attached to the carbon, which is complex to the metal. So, we have a metal complex to a carbon, and this carbon has got two heteroatoms attached to this central carbon atom. And this metal carbon bond has some pi bonding character. So, these set of ligands where you have a heteroatom stabilizing the carbene carbon are in fact called heteroatom stabilized carbene complexes or Fischer complexes, and these Fischer complexes can have either an NR2 group and an OR, or they can have two OR2 groups. This is also equally valid, and so is this alternative where you have two NR2 groups. In this lecture, we are going to specifically concentrate on a set of ligands where you have two nitrogens attached to the central carbon, and in this group of complexes, because of the formation of a ring, you have a cyclic ligand. So, these are called N-heterocyclic ligands, and these heterocycle carbene complexes are extremely stable when they are complex to the metal. So, let us just look at a little bit of the history of these ligands and these complexes, because these complexes have been made only very recently, fairly recently, about 20 years ago. They were discovered only in 1990s, and they have become very popular since then. So, let us take a look at how they were discovered and what led to their popularity. Initially, the interest in these complexes started with the attempts to prepare a free stable carbene. And one way to prepare a stable carbene is to carry out an elimination reaction, where you would start with a molecule which can eliminate a neutral moiety like chloroform. So, if you heat this particular heterocycle to a high temperature, you will eliminate chloroform, and this elimination should lead to a carbene center. This was the hypothesis, and when this reaction was carried out, it was found that you did not form a free stable carbene, but that carbene dimerized rapidly and formed a olefin molecule, and this olefin molecule is pictured here. So, if you can make this olefin, people wondered if this olefin would have some reactivity with metal complexes. And surprisingly, if you treated this dimeric species, dimeric carbene or this olefin with iron pentacarbonyl, you tended to form an iron carbonyl complex, which had this carbene. Now, it is a heterocyclic carbene, and this heterocycle is having two nitrogens stabilizing the carbene carbon, and it is forming a stable iron complex, where the metal carbon distance is in fact less than what you would expect for a iron carbon single bond, and it is more towards a double bond, and we will look at these electronic characteristics shortly. Let us look at another carbene now. This carbene was in fact the main reason why carbenes became extremely popular, because it could be very readily generated from imidazolium salts. The imidazolium salts are stable because they are aromatic species. They are 6 pi electron aromatic species, which could be stabilized and kept in a bottle. They could be easily stored in a bottle because of their stability, and they were stable for two reasons. One is the fact that you have the 6 pi electrons, two lone pairs on the nitrogen, which I am indicating here with red dots, and you also have a pair of electrons between these two carbons. So, that is the next pair of electrons. So, you have a total of 6 pi electrons, and you have a positive charge here, empty orbital. So, you have 5 p orbitals on this ring system, which have got 6 pi electrons, and so it is an extremely stable aromatic system. And furthermore, the positively charged carbon, which has got an empty p orbital, this carbon is stabilized or protected from attack by nucleophiles by this very large adamantile group. This is a popular sterically protecting group, and this adamantile group is the one which protects this carbon from nucleophilic attacks. So, this particular imidazolium cation is extremely stable, and it can be stored in a bottle. Now, this stable cation can be deprotonated by using a base or by using sodium hydride. If you use sodium hydride, the H minus from sodium hydride will now react with this proton, which is here, and this proton will react with this H minus, and it will generate H2, or you can use a base which will remove HX as salt, and that can also lead to a stable carbene moiety. So, this is a stable carbene moiety. It is either generated by elimination of hydrogen and NaX as it is pictured here, or if you use an organic base, you can just remove it as an salt. So, either way you can generate a neutral carbene complex, which is extremely stable also, because it is still an aromatic system. This lone pair, which is pictured here, is stored in the plane of the pi system, and the 6 pi electrons which we talked about earlier are still present perpendicular to the plane of this ring system. You have a total of 6 pi electrons perpendicular to the plane of this ring system, and you have in the plane of the ring, you have a pair of electrons in an orbital, which is like an sp2 hybrid orbital, pointing away from this ring system towards any other species which might come towards this ligand. So, if this is to be used as a ligand, a metal will be approaching this ligand, and this pair of electrons can be donated to this metal. So, this carbene was in fact quite stable. It was prepared and it could be crystallized, and the crystal structure of these ligands could be characterized very readily. And to add to that, one could also characterize the imidazolium salt. So, you have a system which you can compare very readily in terms of geometrical parameters, and which you can use for further reactions very easily. So, let me just summarize the good features of this carbene. This is the carbene that we are talking about. It is sterically protected. So, it has steric protection. It has got a pair of electrons for donation. So, it has a pair of electrons for donation. It has got 6 pi electrons in its ring system perpendicular to the plane of the ring, and that stabilizes it and makes it aromatic. And then it has a vacant orbital on this carbon, and this vacant orbital can be used in terms of electron acceptance from the metal in case it is necessary. So, that will destroy the aromaticity of this ring system, but nevertheless that possibility exists. So, with this introduction, let us just take a look at what would happen if you replace this very bulky adamantyl group with a mesotyl group. That was also enough to stabilize this aromatic ring system. The steric protection was sufficient. In fact, what is interesting is that dimethylphenyl could also be used to prepare this particular ring system and make it stable. So, a variety of R groups that are pictured here, a variety of R groups could be used, dimethylphenyl or isopropyl or tertiary butyl, you name it and you can have it. You can make this imidazolium cation, and subsequently you can deprotonate that imidazolium cation using sodium hydride or a base in order to generate the free and stable carbene. So, this carbene, which is a N heterocyclic carbene, could be stabilized and very easily generated. Not only that, it had this pair of electrons which could be donated to the metal. And as I explained just now, perpendicular to this pair of electrons present on a sp2 hybrid, which makes it a nucleophilic carbon, there is an empty p orbital. This makes the ligand a pi acceptor. From the metal, electron density can now be pushed into the empty p orbital on the carbene carbon, making it a pi acceptor ligand as well as a nucleophilic ligand. This pi acceptance actually arises because you have this type of resonance structure which is present here. This resonance structure is the one which stabilizes the carbenoid species, and this carbon is the one which is now both electron rich and which can accept electron density from the metal. So, not only is the imidazolium cation capable of being a precursor for this carbene, there are a variety of other systems which will also generate this carbene. Here I have pictured a couple of other possibilities. This is the imidazolium cation reacted with a base, and I have already mentioned this, but if you use a base, you would just replace or you would remove the HX molecule which is available here, and you would remove them as a base plus base H plus and X minus as a salt, and you would generate the free carbene. It is also possible now to use a slightly different species. If you have a chloro substituted imidazolium cation, the chlorine can be removed using trimethylsilyl group. The trimethylsilyl group, which I am writing here, is excellent for scavenging chloride ions. Because of its chlorophilicity, it will form trimethylsilyl chloride, and trimethylsilyl chloride can be removed in this reaction, and the X minus can be removed by mercury, and so you would have precipitation of HgX2, and you would form TMS chloride, which is extremely volatile. So, this is a convenient way of making, it is a convenient way of making this neutral carbene ligand, starting with this imidazolium salt by treating them with mercury compounds, and trimethylsilyl chloride is eliminated from this reaction, and it can be readily removed, and the stable carbene is isolated in the pure form, because HgX2 usually precipitates out in the reaction medium, that is dichloromethane or tetrahydrofuran. So, there is yet another method for making this carbene, and here you have elimination of a neutral molecule. This time it is pentafluorobenzene, which is eliminated. C6F5 and H are eliminated from this imidazolium group, or the precursor to the imidazolium carbene, and you can also eliminate a neutral molecule like carbon dioxide. So, here carbon dioxide is eliminated from this species, this carboxylate imidazolium compound, and you can form this neutral carbene. I am showing you so many methods of making this carbene molecule, because the ability to make this carbene is in fact a key point. It is a key feature of this whole chemistry, because you can make this carbene readily. It is available for chemists to use in a variety of systems and study them very easily and very effectively. The last method is to remove a sulfur atom from this urea derivative, and that can be done with reactive potassium. You add metallic potassium and you can eliminate potassium sulfide, and because you have eliminated potassium sulfide, you again form a neutral carbene, and this potassium sulfide can be just removed through filtration. So, here is a ligand which is extremely easy to generate through a variety of methods, and it is possible to make them in good yield, and so it's become an extremely popular ligand. And very often it is possible to characterize both the imidazolium salt and the free carbene in using crystallography. In this particular picture, I am showing you the picture of a ligand where you have the mesytyl group, two methyl groups are here attached to the phenyl ring, and that is the group which is providing steric protection for this carbon, which is right here, this carbon which is positively charged. In this structure, you have of course a proton here, which is pictured in white, and you have the counter ion, which is your X minus. Now, this imidazolium salt can be deprotonated, as we have just seen, and you can generate the carbene. The reason for showing these two pictures is to emphasize the very close similarity between these two structures. There appears to be very little change when you go from the imidazolium salt, which is pictured here, to the carbene, which is pictured here. The structure seems to be extremely similar, and it is now possible for you to use this carbene carbon with the negative charge on the carbene carbon, which is actually located as a pair of electrons on this carbon in the plane of the ring to form metal complexes. I have shown you here a three-dimensional model or a space filling model of the carbene. Reason for doing this showing you the space filling model is to show you that the carbene carbon, which has been selected and shown using this yellow which has been marked in yellow in this particular picture. This as C1, this carbene carbon is visible to us and it is visible to the metal also to form a nice complex. But at the same time, you have substantial steric protection because of the presence of these bulky groups on either side of the carbene carbon. So, let us just look at some chemistry which follows the preparation of this carbene. These carbenes, which have been generated by various means, can be readily complex to a metal, and in some instances they can be reacted. The imidazolium cation can be directly reacted with a metal salt in order to generate the carbene complex. So, that is yet another advantage. Not only do you have the precursor to the carbene, but you can use the carbene itself to form the complex. So, in both instances, you can form nice carbene complexes with a metal salt. So, here you have, in this particular picture, you have the palladium atom, which was generated using palladium acetate. In the presence of sodium iodide, it forms a complex where you have the iodo group, which is complex to the palladium, and the carbene, which has been generated in the presence of this palladium acetate by removal of HOAC. So, the acetate group comes from here and the proton comes from here, and so you can eliminate HOAC to generate this carbene in the presence of the palladium acetate. So, the palladium forms a dimeric species, and you can break this dimeric species using yet another ligand. If you add another ligand such as triphenylphosphine, you can form a monomeric species starting with this dimeric species. I am showing you this simple chemistry, which is in fact a general principle to move from a polymeric system to a monomeric unit. You normally add a second ligand, which is a fairly good and strong ligand, to break the dimeric species and to form a monomer. So, this turns out to be a general principle for forming a monomeric complex starting with the dimer. But this also tells you that the triphenylphosphine does not displace the carbene ligand, which is complex to the metal. Instead, it only breaks this dimeric bridge and it forms the monomeric complex. So, let us now form look at the structures which are formed using these carbenes, and before doing so, I will give you just a few more examples. Here is yet another example where once again you have used mercuric acetate in order to generate a carbene. This time you have mercury coordinated to two of these carbene units in a linear fashion, as mercury 1 normally does. You can have this mercury complex where you have two carbenes which are both interacting with the metal atom. Here I have pictured a chromium carbonyl complex, which is a carbonylate, and this carbonylate reacts with the protonated imidazolium salt. Once again, this is an example where the imidazolium salt can be directly used for generating the complex. And here you have the carbene, which is having a positive charge on this ring, but this is in fact delocalized all over this ring system. So, you have this positive charge delocalized on this ring system, and that is complex to the chromium. And as a counter ion, you have an X minus, which is coming from this imidazolium salt that we used to prepare this complex. So, you can have very interesting and very nice complexes where carbonyl group is attached to the metal atom and also a carbene is attached to the metal atom. let us look at some of the geometrical changes that occur in N-heterocyclic carbenes a little bit, because this will give us an insight into what is going on in a carbene complex. If you look at the imidazolium salt, the imidazolium salt is pictured here on the leftmost side of the screen, and this imidazolium salt, if it is deprotonated, forms a carbene. If it was a triplet carbene, then one would expect this ring system to have an angle of 109 degrees, or this carbon to have an angle of 109 degrees. But we know that it is something more of a singlet carbene, where the two electrons are in a plane perpendicular to the plane of the ring. So, this angle which I have pictured here is more like 120 degrees. So, this angle is close to 120 degrees, and the lone pair or the pair of electrons from the carbene is localized on an sp2 hybrid. And because of this delocalization of this double bonds, you now have a angle which is close to 120 degrees and a carbon nitrogen distance which is shorter than what you would expect for a carbon nitrogen single bond. So, this delocalization has got two effects. A, it shortens the CN double bond, CN bond, and makes it a CN double bond, and it also has this effect of having an angle similar to 120 degrees. Now, when you form a complex, so this is the carbene, this is the neutral carbene which we are talking about, and when it is complex to the metal atom, it forms a cyclic ring system, cyclic or delocalized ring system, where this charge is now delocalized on this ring system, and that leads to a metal carbon single bond. But as I told you before, it is possible to push some electron density into this ring system through the metals filled orbitals into the rings vacant orbitals, and this will partially destroy the aromaticity of the heterocyclic carbene ring system, but nevertheless it stabilizes the complex as a whole. So, these are some of the small changes that happen when you move from the partial double bond character to the metal complex. Here you would have some small changes in the angle. Usually the angle becomes slightly larger, it becomes closer to what you would expect for 109 degrees, and it and the double bond is partially back. So, you have a greater double bond character between the metal and the carbon, and also delocalized bond between the carbon and the nitrogen. So, let us look at now the pi donation. Why did we say that it is possible to push electron density into the ring system? There is sufficient evidence for this particular phenomenon. In fact, if you have simple hexacarbonyl chromium, you would have a Raman stretch corresponding to 2108 centimeter minus 1, and when it is complex to a heterocyclic carbene, then the carbonyl stretching frequency decreases. A decrease in the carbonyl stretching frequency is indicative of the fact there is greater electron density on the chromium. So, you now have greater electron density on the chromium compared to what you had when you had CrCO6. In CrCO6, the Raman stretch was 2108 centimeter minus 1, and now it is decreased further to 1972 centimeter minus 1 because of the presence of this N-heterocyclic carbene. Now, one has to compare it with other ligands, and we do that here by looking at a Fischer carbene. This is an example of a Fischer carbene. Fischer carbenes also have the ability to push electron density into the chromium, and they in fact do that much more effectively. For an example, we have this Fischer carbene stabilized chromium pentacarbonyl complex, and this has got a stretching frequency of 1953 centimeter minus 1. We are always talking about the stretching frequency of the carbon monoxide, which is trans to the ligand which we are discussing. So, this is the ligand that we are discussing, this carbene carbon complex, and here we are talking about this N heterocyclic carbene, and we are talking about the trans carbene carbon monoxide, and the trans carbon monoxide has a stretching frequency of 1972 centimeter minus 1. And in the case of the Fischer carbene, we have a stretching frequency of 1953 centimeter minus 1. So, these two ligands, they pump electron density into the metal, and that is responsible for the lower stretching frequency compared to CrCO6 itself, where the stretching frequency was 2108 centimeter minus 1. So, we always compare, we have a reference complex, and the reference complex for us in this case is CrCO6, and we put a carbene in the system and then look at the carbon monoxide stretching frequency of the trans carbon monoxide. So, one way to look at these electronic effects is to look at a series of complexes. It is better to look at a series of complexes, because we are not looking at an isolated incident, but a phenomenon where you have very clear indication of electronic effects. Tolman did this with a series of complexes which he could easily prepare, starting with nickel tetracarbonyl. So, he took nickel tetracarbonyl. So, that is NiCO4. NiCO4 was treated with a ligand, and he formed this particular complex. And this complex now has got 3 carbon monoxides attached to the nickel and a particular ligand L, which we want to discuss. And he looked at the carbon monoxide stretching frequencies of these 3 carbon monoxides. Because you have a C3 symmetry, you would end up with 2 different stretching frequencies, and he took the average of both, and the symmetric stretching frequency that you would have is the one that he parameterized as Tolman's electronic parameter. Tolman was a person who carried out this experiment first, and this average CO stretch for the carbon monoxides which are trans to the ligand, not really trans, but on the other side of the nickel. So, the symmetric stretching frequency of these 3 carbon monoxides is called the Tolman's electronic parameter. Now, let us take a look at what would happen if you have carbon monoxide itself. So, that is nickel tetracarbonyl, and then this stretching frequency is 2060. The actual stretching frequency in dichloromethane is 2057, but I have rounded it off to 2060 centimeter minus 1, and it is always convenient to have round figures in order for us to remember it easily. So, just remember that nickel tetracarbonyl has a stretching frequency of 2060 centimeter minus 1, and when you substitute it with the ligand, then you have a change in the stretching frequency, and this stretching frequency is now something that we are going to call as Tolman's electronic parameter. When you have a ligand which donates a lot of electron density to the metal, to the nickel, then the stretching frequency would go down. So, the greater the electron density given by the ligand, when this electron density donation goes up, the stretching frequency would go down. So, the Tolman's electronic parameter has an inverse correlation with the electron donation from the ligand. So, this can be done for a wide series of ligands, and Tolman chose NiCO4 because it was easy to do spectroscopy with it, and it is also easy to synthesize these metal complexes very readily, starting with nickel tetracarbonyl. So, here is the Tolman's electronic parameter given for a series of ligands. I have given here 3 different N heterocyclic carbenes, and you will notice that this is the type of carbene ligands that we were talking about, and this has got 2 nitrogens stabilizing the carbon atom bearing the lone pair. But you can also have a sulfur or an oxygen. Here we have a sulfur and here we have an oxygen which is stabilizing the carbene carbon. In all these cases, you have the carbene carbon stabilized by a heteroatom. And when it is complex to nickel tricarbonyl, as in this complex that we are talking about, then the stretching frequency of these 3 carbon monoxides, the symmetric stretch goes down to 2060 centimeter minus 1, or it is close by, as in the case of sulfur you have 2061, and in the case of this NN dimethyl stabilized heterocyclic carbene you have a frequency of 2065 centimeter minus 1. These are very close to carbon monoxide stretching frequencies, and so that is indicative of the fact that the pi accepting character of these ligands are similar to carbon monoxide. So, if you by comparing the Tolman's electronic parameter, one would be able to identify whether the ligand is capable of pi acceptance, whether the ligand is capable of pi accepting character, whether it has pi accepting character, or whether it has sigma donating character, and which of these characteristics is predominating in the complex. So, let us take a look at some of these complexes in the N heterocyclic carbenes. When you have a mesetyl group which is stabilizing the imidazole, then the stretching frequency in fact goes down to 2051 centimeter minus 1. So, here you see that it has gone down further from 2060 centimeter minus 1. So, the pi accepting character is indeed there, but nevertheless the sigma donation property of this imidazolyl mesetyl stabilized imidazolyl carbene is better. The sigma donation is much better in the case of the imidazole ring which is bearing the carbene carbon. If you have, instead of a mesetyl group, if you have an isopropyl group in the imidazolyl carbene carbon, then you end up with a frequency which is 2052 centimeter minus 1. You will notice that all of these 3 have got very close stretching frequencies, and these are indicative of the fact that the imidazolyl group is capable of giving a large amount of electron density, much more than carbon monoxide, to the nickel tricarbonyl complex. Now, if you want to compare it with the phosphorus bearing complexes, then you will notice that the phosphines also have got good electron donating capability, and they have poorer pi accepting characteristics compared to carbon monoxide. This is indicative of 2 factors. One is the fact that they are poorer pi acceptors compared to carbon monoxide, and the other is the fact that they donate more electron density to the metal compared to carbon monoxide. So, here are a series of phosphorus ligands, and all 3 of them are having very similar stretching frequencies, except for PPH3, this is triphenyl phosphine, which has got a stretching frequency much higher than the complexes that the ligands that we are discussing here. Triphenyl phosphine has got a stretching frequency of 2069 centimeter minus 1, and that seems to indicate that in this particular instance you have PPH3 which is giving less electron density compared to these ligands to the metal, and it has got very good pi accepting characteristics as well. When you have an imidazolyl group which is flanked by 2 nitrogens bearing cyclohexyl groups, then the stretching frequency has gone down significantly below 2060 centimeter minus 1, and it is 2049 centimeter minus 1, and this seems to indicate that you have very good electron donation from the imidazolil carbon to the nickel complex. So, this way of comparing a series of complexes and looking at the stretching frequency has helped in quantifying the type of electron donation or the type of electron accepting properties of the ligand. It is also possible for us to draw it or show it in a graphical form. Here I have tried to show it in a graphical form. The frequency is increasing in this direction, in the direction of this arrow. So, the frequency is increasing in this side, and the electron density that is being pumped into the metal is increasing in this direction. I told you that there was a inverse correlation, and in fact, there is an inverse correlation between the electron donation and the frequency that you observe for the 3 carbon monoxides. So, Tolman's electronic parameter, which is abbreviated as TEP, is plotted here. This is TEP, and it is increasing in the direction from right to left, and the electron donation is increasing from left to right. So, if you have cyclohexyl groups, these are cyclohexyl groups, and cyclohexyl groups are obviously electron donating groups on the they are present on the nitrogen. Then the electron donation seems to be the maximum, and the stretching frequency has gone down all the way to 2045 centimeter minus 1. These are close, they are rounded off to some close numbers, so that you can easily remember them. Here is another one where you have an adamantyl group, but the ring system that is bearing the carbene carbon has got some unsaturation. So, the frequency has got a higher number. As you have a change in the ring size, then you have a change in the amount of electron donation to the metal atom. So, if you have a large ring, the electron density that is moved from the ligand to the metal seems to be high. So, if you have a 7-membered ring, here is a 7-membered ring, that seems to donate more electron density compared to a 6-membered ring. Here is a 6-membered ring, and then you have a 5-membered ring here. So, the 7-membered ring donates more electron density compared to the 5-membered ring. You will also notice that we can have unsaturation in the ring system, and you can also have a saturated ring system. Both ways you can have stable carbenes which are attached to the metal atom. But in general, as the angle increases, as the angle NCN angle is the one that we normally talk about, as this NCN angle increases, you have greater and greater electron density donated to the metal atom. So, it is not always possible to prepare the nickel tetracarbonyl complex, and so I have pictured here the iridium complex and a rhodium complex, which can be easily generated. These are similar to Vasca's complexes, and you have 2 carbon monoxides attached to the metal atom, and the carbon monoxide which is trans to the N heterocyclic carbene, which is this carbon monoxide. This stretching frequency is very typical or is affected to a great degree by the ligand which is present in the trans position. So, that is the N heterocyclic carbene that we are going to talk about. So, depending on the electron density donated by the N heterocyclic carbene, this carbon monoxide stretching frequency changes. The advantage in using this metal complex or this metal complex system is a fact that you have only one CO stretching frequency that needs to be observed. So, this stretching frequency has been measured for a series of ligands, and if you plot the Tolman's electronic parameter on the x axis. So, this is the Tolman's electronic parameter, and you plot the iridium complexes stretching frequencies on this axis, you find a linear correlation. So, that is just indicative of the fact that these two frequencies are related. The electronic effects that you observe in the nickel complex can also be observed in the iridium complex. If you have greater electron density donated to the metal from the N heterocyclic carbene, then the stretching frequency goes down. So, as the TEP increases, electron density donation decreases. So, you can in fact have these linear relationships quantified, and they give us a very good confidence that in fact the type of relations that we are observing are in fact proper scientifically valid relationships, which are very clear indicators of the electronic effects of the ligand. Now, it is possible to tune the electronic parameter in a variety of ways. A very ingenious way of tuning the electronic parameter is to not use electron withdrawing groups, but to remove an electron completely, say using electrochemistry. And it is possible to do this in the case of these ferrocene stabilized ligands. So, in fact, Fc is indicative of this ferrocenyl group. Fc is indicative of this ferrocenyl group, and if you have two ferrocenyl groups substituted on the nitrogen, then you can have a very nice ferrocene stabilized carbene. And this ferrocene stabilized carbene can be attached to the iridium 1 complex, and you can look at the stretching frequency of this carbonyl, which is carbonyl group, which is trans to the heterocyclic carbene. So, you can now remove an electron from this complex, and this electron is removed from the ferrocene moiety right here. So, you can have a reduced species, or you can have an oxidized species. This is an oxidized species. So, this is the oxidized species, and this is the neutral form or the reduced form. So, you can compare the Tolman's electronic parameter or the iridium carbonyl stretching frequency, and you will notice that the oxidized form has got a difference of 11 to 13 centimeter minus 1 between the system which is neutral and the system which is oxidized. When you oxidize it, then the carbene becomes electron poor. If the carbene is electron poor, then it donates less electron density. If the iridium has less electron density, then less electron density is pushed onto the carbon monoxide. If less electron density is there on the carbon monoxide, then the stretching frequency is not reduced significantly and the frequency is increased. So, the oxidized form has got a stretching frequency of 11 to 13 centimeter minus 1, greater than what you have for the neutral form. So, the neutral form has got less stretching frequency or a lower stretching frequency, and the oxidized form has got a higher stretching frequency. Another interesting complex has also been made, and this is a similar iridium complex where you have a carbon monoxide trans to this ferrocene stabilized unit, but this time the ferrocene units are in fact attached directly to the nitrogen. A very ingenious way of controlling the electronic effects, but unfortunately the difference between the oxidized and reduced forms are mostly in the range 11 to 13 centimeter minus 1 in all these cases. And so, the type of electron density change that you have on the carbon, the carbene carbon, is not very large. For a comparison, I have given here the change that occurs between PPH3 and PCY3. CY is cyclohexyl group, and in fact, it is much more electron donating compared to PPH3, and that difference is also 11 to 13, approximately in the range of 12 centimeter minus 1. So, this is a surprising phenomenon, but nevertheless, it is a very interesting factor that has been observed. So, people have been able to observe this electron density being donated from a carbene carbon to the metal in a variety of different ways. Another easy way to do it is to look at the carbon 13 chemical shift that you can observe readily for diamagnetic complexes. As long as you have an organometallic system which is diamagnetic, and most organometallic complexes are in fact diamagnetic, you would be able to observe the carbon 13 chemical shift. And that chemical shift changes when you have a neutral carbene and when you have a complex which is where the carbene is attached to the metal atom. The chemical shift is usually shifted upfield by 30 to 180 ppm, and this chemical shift is indicative of the fact that there is electron density which is shielding the metal atom. The metal atom's electron density is shielding the carbene carbon and giving it some extra protection from the external field, and that is why you have to go upfield in order to observe these carbene carbons. So, this is in fact the type of chemical shift changes that you observe in the carbene carbons. Here I have two mesetyl groups attached to the nitrogen, and the only difference between these two ring systems is that this ring system is unsaturated and this ring system is saturated. And you can see that there is about 20 ppm chemical shift difference between these two units. And people have tried to derive an electronic parameter based on the chemical shift of this carbon versus the ligand which is present in the trans position. So, if you can look at vary this ligand and measure the chemical shift of the carbene carbon which is in the trans position, you would be able to derive an electronic parameter. But this is not been as popular as Tolman's electronic parameter. So, we will not discuss this further, but suffice it to say that the electron density changes are sensitively reflected in the chemical shift of the carbene carbon. So, with this we will close this lecture, and we will discuss the steric phenomena that is associated with N heterocyclic carbenes in the next few lectures. I will now summarize what we discussed so far by going to end. We have discussed a series of N heterocyclic carbenes. This is a neutral ligand with good pi accepting capability. It has got a p orbital which is substantially large in character, and it is able to accept electron density from the metal d orbitals. It has got good sigma donation properties, and we have seen this from the Tolman's electronic parameter. And because of the steric properties which can be tuned, which we will see later, both the electronic and steric properties are substantially modifiable, and so this tunable character gives it a very great advantage. The ligand can be easily synthesized in situ, and that makes them the N heterocyclic carbenes superheroes as ligands.